Any questions before we continue? Now, basically, last week we started the study of dielectrics, and this week we are looking at a particular case of dielectrics, the dielectrics so-called linear dielectrics. Now, what we mean by linear dielectric is a dielectric in which the polarization is directly proportional to the electric field, and similarly the displacement field is also directly proportional with the electric field. So this is what we mean by linear dielectric. And well, this is kind of the missing link for us to solve for the electric and the displacement fields. If you remember, the electric field always satisfies the curl of E is equal to 0. The displacement field satisfies the divergence of the displacement field is 4 pi rho. So in principle, a priori, before solving the problem, we know the free field, free charges. We don't know what the bound charges are. So these are the two equations we need to solve. And to solve for a vector field, we need to know both the divergence and the curl of a vector field. But here we have the electric and the displacement field. We know the divergence of one and the curl of the other one. So we had to somehow find a relation. And linear dielectrics, these linear relations over here give us that connection between the two. We also studied the energy stored in a linear dielectric, and we had seen that in a linear dielectric, the energy stored was equal to 1 over 2 E dot D integrated over the volume. So kind of this 1 over 2 E dot D is our energy density. But keep in mind that this, before we also studied the energy stored in an electric field. That was the work that we had to do in order to bring all the charges to their final positions. Now, this work done is the amount of work that we have to do in order to bring all the free charges to their final positions in the dielectric. The dielectric is already there. But that is the energy that we can store and we can use later on. If we are not planning to break up the dielectric, the energy that the dielectric has, the self-energy of the dielectric, let's say, is something we cannot really extract. So this is the amount of energy that we can extract from our system. And then we looked at the capacitors on Monday that has dielectrics inside. And if the dielectric completely fills the capacitor, we had seen that the capacitance is increased by this relative permittivity or the dielectric constant over the free K. So in a given dielectric, without changing the distance and the areas, by inserting a dielectric, you can increase the capacitance of your system. And you can call this increase can be quite significant. And finally, we had seen that if you have such a system, a capacitor and a half-filled dielectric. In this case, if you remember, we first calculated the work done, the energy stored in this system as a function of this length. And once we know that length, we could calculate the force exerted on the dielectric. This is by just taking its derivative. And at the end, this resulted in a force in this direction. This is the direction of the force that the capacitor exerts on the dielectric. So the capacitor kind of just tries to pull in the dielectric. And the origin of this force is these fringing effects. So you see, inside the electric field is more or less uniform in the vertical direction. They cannot create a horizontal force. But at the edges, there will be these fringing fields, and hence the electric field is not perpendicular, it's horizontal. It also has a horizontal component. And that horizontal component exerts force on the bound surface charges, which are created due to the polarization of this dielectric, pulling it inside. And that was kind of where we had left. Now, any questions up to this point? Now let's look at some examples involving these dielectrics. Boundary value problems. So let's see, we had studied as a boundary value problem, for example, the method of images. So let's see if we have a similar case over here. Well, without actually going for an example, you see, if you remember what we had done before, for example, we had this sphere, this dielectric sphere in a uniform electric field. Let's look at this one. Outside, there's a uniform electric field. Far away from our dielectric, we put some dielectric inside. So what is the new electric field? We know that this electric field will polarize the medium. Hence, due to this polarization, there will be an additional electric field modifying the applied electric field. So the boundary conditions we have for the potential. What is V0? The potential corresponding to this uniform electric field. You see, E is equal, E0 is some number in the Z direction. This is our Z axis. So what is the corresponding potential? Minus, if you integrate it over Z, you basically get minus E0Z. So this is the potential corresponding to that field. I'm choosing Z equal to 0 plane as the 0 potential plane. And in spherical coordinates, we can write this as E0 R times cosine theta. So this is what the potential should look like at far away distances. Now let us write in this problem, we also solved this problem for a conductor. And if you remember, for a conductor, what we had done is inside we already know that the potential is constant. Outside there is a potential. And so the potential should be continuous. That was one condition we had for the unknown coefficients. And the normal derivative should have some kind of a discontinuity from which we could find the charge density also. Now let's do a similar thing over here. Let's first, well, of course, since this is a dielectric, we have an electric field also inside. The potential inside is non-zero. So let's look at that one. V1, this is region 1. This is region 2. I will use separation of variables in spherical coordinates. This is my origin. My z-axis is horizontal in the direction of the electric field. X-y-axis, well, you can pick up any direction that you like. And the potential inside the sphere should have this form. This is the potential inside. Well, of course, there is also, in spherical coordinates, the general solution of the Laplace's equation is that we also have this BL over R to the L plus 1, but the potential has to be finite at R is equal to 0. So that term cannot appear. Now, of course, this is the solution of the Laplace's equation inside. Outside, let me write it in this form, minus E0 R cosine theta. Asymptotically, this should be, this satisfies my Laplace's equation, this term only. So let me add another term, unknown term, BL over R to the L plus 1 times PL cosine theta. Now there is also an AL R to the L term in this sum, but I know that since I have already separated the asymptotic form, what remains has to go to 0 as R goes to 0, infinity. But this AL R to the L term over here doesn't go to 0. So that term cannot appear. L from 0 to infinity. By the way, L is... okay, these are the solutions of the Laplace's equation, but do I know that the potential satisfies the Laplace's equation? Let's see if the potential should satisfy the Laplace's equation. We know that curl of electric field, curl of E is equal to 0, and hence the electric field can always be written as the gradient of some potential. This is always true, whether we have matter or not, doesn't really matter. Now the displacement field is epsilon times the electric field, and the divergence of the displacement field in this system is, what is the divergence of the displacement field in this system? Why?
Constant.
What is constant? Well, we don't know whether the displacement field is constant or not. This is the electric field. Electric field far away from my sphere is constant, but the sphere will modify the electric field, and hence the electric field will not be a constant.
Rho free.
There's no rho free. We didn't put any charges. There are these charges at infinity that create this electric field, but I'm just looking at this region. In this region, there are no free charges. There are, of course, bound charges in the dielectric, but the divergence of the displacement field gives me only the free charges. Hence, this is equal to 0. There are no free charges. Well, I also know that the displacement field is epsilon times E. So the divergence of epsilon times minus the gradient of V, this is equal to 0, or the divergence of epsilon times the gradient of V, this is equal to 0. Well, still this doesn't tell me that the potential satisfies the Laplace's equation. In fact, since there are bound charges, the potential does not satisfy the Laplace's equation everywhere. But you see, we have in region 1 and 2, epsilon is constant. Epsilon doesn't change in region 1 or in region 2. It only changes as we go from region 1 to region 2. In region 1, it is just epsilon. In region 2, it is 1, the dielectric constant. It's vacuum, so it has dielectric constant 1. So, since epsilon is constant in both of these regions, I can take it out of the divergence, out of the derivative, and what remains is epsilon times the Laplacian of V is 0, or the Laplacian of V is equal to 0. This is true only in region 1 and also in region 2, but not at the boundary. It will have non-zero value because we will have surface charges on the boundary. So let's see, these are our potentials. Inside and outside my sphere. Now, first of all, I know that the electric field should be, the potential should be continuous across the boundary. So V1, when the R is equal to the radius, should be equal to V2 when R is equal to the radius. Well, let's just put their expressions. L from 0 to infinity, AL R to the power L PL of cosine theta should be equal to minus E0 R cosine theta. Well, cosine theta is P1 plus L from 0 to infinity BL over R to the L plus 1 PL of cosine theta. Well, on both sides I have expressions, some linear combination of these Legendre polynomials. I know that the Legendre polynomials are, well, one thing I know, complete. Any function can be written as any function that is defined between -1 and 1 can be defined in terms of the Legendre polynomials. Furthermore, if two such linear combinations are equal, then their coefficients have to be equal on both sides. So for L is equal to 1, on the left-hand side I have A1 times R. This is the coefficient of P1. And on the right-hand side, the coefficient of P1 is minus E0. Now this is capital R. Plus B1 over R squared. This is for L is equal to 1. For other L's, I have on the left-hand side, I have a L R to the power L, which should be equal to BL over R to the power L plus 1. This term only contributes to L is equal to 1. So this is one set of equations relating our unknown constants AL and BL.
Hocam şimdi P1 zaten kosinüs teta değil mi? Sağ.
True. It's not constant.
Olmayınca yok oluyor.
It doesn't disappear. You say this is P1, but what I am saying is the coefficient of P1 here should be equal to the coefficient of P1 here. The coefficient of P2 here should be equal to the coefficient of P2 here. This term only contributes to the coefficient of P1. It doesn't contribute to the coefficient of P2, neither P3, neither P4. So that is why only in the case of L is equal to 1, on the left-hand side I have this one, on the right-hand side there is a contribution of this one. This term doesn't contribute to the coefficient of other Legendre polynomials. Where? This is, you say this is P1. This is the term, this is the asymptotic form. This gives us the asymptotic form, this term. This goes to 0 at infinity. And this is proportional to, the P1 over here is proportional to 1 over R squared. You see, in spherical coordinates, the general solution of the Laplace equation is, assuming it doesn't depend on the phi coordinate, it's AL R to the L plus BL divided by R to the L plus 1 times PL of cosine theta. You see, each PL basically has two constants. But you see, this constant goes to, this term goes to 0 at infinity, this term does not. So that's the distinction between the two. So what we said over there, I already know that V2, the potential outside for R very large, should go to this term. Should become this value, should have this value. That I already know, that's given to me. What I add to this term should go to 0 at infinity. But you see, if you look at the general solution, this term doesn't go to 0 at infinity. It either diverges or it is constant. So this term shouldn't appear in the part that goes to 0. Now, then we have this other boundary condition. You see, the curl of E equal to 0, this equation tells me that the parallel component of the electric field is continuous. which basically tells me that V is continuous across the boundary. Then there is the other equation. Divergence of D, in general, it is it's rho bound, rho free, sorry. It's equal to rho free. And this equation basically tells me that the outside minus the inside is equal to the free charges on the boundary multiplied by the normal direction. Well, basically these, no, this is not true. The perpendicular direction of the outside minus the perpendicular direction of the inside is equal to sigma f. But in our problem, there's no free charges on the boundary. So in our problem, this should be equal to 0. But the perpendicular in our problem, our problem is this one. We have a sphere. The perpendicular is equal to epsilon times E perpendicular. E, the electric field, the perpendicular component is the radial component. We have a sphere with origin at the center, so the component perpendicular to the surface of the sphere is in the radial direction. But this is equal to minus epsilon dV by dr. So this product has to be continuous. Now in region 1, epsilon is epsilon. You see, if you remember back our problem, region 1 is inside our dielectric. The dielectric constant is epsilon. In region 2, there's no dielectric. The dielectric constant is 1. Of course, this is to be satisfied on the boundary. So this will give us our second set of equations for the two sets of unknowns we have. So let's use them. So these are our potentials. Let's take their derivatives with respect to r. So epsilon times L from 0 to infinity, AL, L, r to the power L, PL of cosine theta. This is the left-hand side. This should be equal to minus E0 times cosine theta minus L from 0 to infinity, L plus 1, BL over R to the L plus 2, PL of cosine theta. And remember, cosine theta is P1 of cosine theta.
Şurada L eksi 1 olmayacak.
You mean this one? Yes, you're right. This is L minus 1, and this is capital R. Again, let's write the coefficient of the P1 cosine theta on both sides. On the left-hand side, we have epsilon A1 times, well, there's no R. Epsilon A1 is the left-hand side. On the right-hand side, the coefficient of P1 is minus E0 minus B1 minus 2B1 divided by R cubed. This is one equation we have. And for L different than 1, we have epsilon AL times L R to the L minus 1. This should be equal to minus L plus 1 BL divided by R to the L plus 2. We had these two previous equations. Well, look at this equation over here, the last one, and the second one above. Well, this basically tells me that AL and BL have the same sign. They are both positive or they are both negative. That equation tells me that AL and BL have the opposite sign. But two numbers can have the same sign and also the opposite sign only if they are both 0. So this is equation 1, this is equation 2, this is equation 3, this is equation 4. 2 and 4 tells me that AL is equal to B is equal to 0, BL is equal to 0, if L is not 1. Well, that kind of simplifies my life. In this sum of infinitely many terms, only one of the terms is non-zero. Now let's look at the coefficient of that term. You see, on one hand, equation 3 tells me that A1 is equal to minus E0 plus B1 over R cubed. I just divided left-hand side and the right-hand side by R. And then equation 1 tells me that epsilon times minus E0 plus B1 over R cubed. This should be equal to, use epsilon times A1, the left-hand side, minus E0 minus 2B1 over R cubed. So let's simplify it a bit. We have epsilon plus 2 times 1 over R cubed, B1, should be equal to epsilon minus 1 times E0. Or B1 should be equal to R cubed epsilon minus 1 over epsilon plus 2 E0. This is our B1. Now I can determine A1. You see, A1 is this number over here. It's related to B1. Now we had calculated B1. This is minus E0 plus epsilon minus 1 over epsilon plus 2 E0. So this is minus epsilon minus 2 plus epsilon minus 1 divided by epsilon plus 2 times E0. Or A1 is equal to minus 3 over epsilon plus 2 A0. Now E0. So we also know A1. We already know that A0, A2, A3, A4, etc., they are all 0. B0, B2, B3, B4, they are also all 0. So these are the only ones remains. So we know the potential inside. This is equal to A1 times R to the 1 times P1 of cosine theta, which is equal to minus 3 over epsilon plus 2 R cosine theta minus 3 over epsilon plus 2 Z times E0. Well, you see, inside there's a uniform electric field still. Since the electric field is uniform inside, the polarization is uniform inside, so this is nothing but a uniformly polarized sphere. Let's look at the outside V2. V2 was minus E0 R cosine theta plus B1 this is B1 R to the power R squared times P1 cosine theta. This is minus E0 R cosine theta plus epsilon minus 1 over epsilon plus 2 E0 R cubed over R squared P1 of cosine theta. So you see, the first term is already the applied electric field. This corresponds to the external electric field. And this is basically the electric field of a pure dipole, potential of a pure dipole. So if you remember last week, we had studied the electric field created by a uniformly polarized sphere. And if you remember, we just said that it was similar to the problem of two homogeneously charged spheres overlapping, and then we took the limit that their overlap was complete. So they're just one over on top of the other one. And we took the limit that the distance between their centers goes to 0 and their volume charge density goes to infinity, creating a uniform dipole. And for an outside observer, we said that this just behaves like a pure dipole. Well, that is what we have actually found over here also. There is an external electric field, external potential, plus the potential created by a pure dipole at the origin. And that dipole created a uniform polarization corresponded to a uniform electric field in our system. So this is basically it. So we have an external electric field which is already uniform, plus the electric field created by this polarization which is also uniform. So this is it. You see, this is the electric field in region 1 is just minus the gradient of this one. It is 3 over epsilon plus 2 in the direction of the original electric field. And keep in mind that this dielectric constant is always larger than 1. So this ratio is smaller than 1. The electric field inside the dielectric is less than the applied electric field. And this total electric field is obtained by the superposition of the external electric field, which is just E0, plus the electric field created by this dipole, by the polarization of our system. So the polarization of our system also should create a uniform electric field. So you see this is E external, which is E0, plus electric field due to the polarization. And hence this electric field due to the polarization is actually 1 epsilon minus 1, no, 1 minus epsilon divided by epsilon plus 2 E0. It is also uniform. This is in the opposite direction to the applied electric field. Furthermore, it is also uniform. This doesn't depend on this doesn't change from point to point. This is a constant. This is also a constant. But we had already seen that if you have a uniformly polarized sphere, the electric field it creates is uniform. So if we have a uniformly polarized sphere, so this basically corresponds to negative charges here, positive charges here. So it created a uniform electric field in the opposite direction, inside. Outside, it was just the electric field of a ideal dipole. Now, on top of this, we have this uniform electric field. And the total electric field corresponds to these potentials in rectangles. So this is the potential of the uniform electric potential corresponding to a uniform electric field. Here we have the potential corresponding to the external electric field plus the potential corresponding to a pure dipole outside.
What are the parallel and perpendicular components of the electric field?
So let's see, we have this arbitrary surface. At this point, there will be an electric field in some direction. Now at the same point, I can consider this line that is perpendicular to my surface, and this line that is tangent to my surface. And at that point, I can consider the two components of the electric field. This is what I call the E perp. This is what I call the E parallel. Well, for any vector field, in fact, I can just, at any point, I can always consider the perpendicular direction to the surface and parallel tangent direction to the surface. The component of the vector field tangent to my surface is E parallel. The component perpendicular to my surface is the perpendicular component. Now, do you remember the connection between curl of E equal to 0 and the change in E parallel is equal to 0? And the divergence of D being rho free to the change in D perp is equal to sigma free. Do you remember how we relate, how we obtain from this equation, how do we obtain this relation? So basically what we did to obtain, let's say, from divergence of D to the discontinuity in the perpendicular component, just to refresh your minds, we had assumed a cylindrical Gauss surface and we applied the Gauss law. The area was A, so the charge enclosed in the surface was equal to sigma F, QF enclosed. And then when we set the height of this cylinder to 0, when we took the limit that the height would go to 0, we only received contribution from the top part and from the bottom part. the area vectors are perpendicular to the top and the bottom. So we this integral, the Gauss integral, remember it was this one. ds is perpendicular to the area, so this scalar product just gave me the perpendicular component of this displacement field. And hence, we could conclude that by dividing by the area both sides, that the perpendicular component of the displacement field across the surface need not be continuous. And then the discontinuity is equal to the free charge density. And similarly, for the curl of E, we apply the curl of E equal to 0. This also tells me that the integral of the electric field around any closed loop should be 0. So since it is true for any loop, we consider this rectangular loop. We first took the limit that this side goes to 0, and then dl vector over here is parallel to the surface, so the scalar product gives me the parallel component of the electric field. And since this integral is always equal to 0, this told me that the parallel component of the electric field as we cross this surface changes continuously. There is no jump. But the displacement field can jump from one value to the other value as we are crossing the surface.
Hocam peki o yüzeyde bir tane küçük delik olsaydı ne olacaktı?
Well, you see, when we are talking about these surfaces, these are actually mathematical surfaces. It doesn't have to be some material surfaces. For any surface, these should hold. By meaning that there's a point over there where there's a hole. Well, that is just my mathematical surface is still continuous, but at that point there is no charge. Since the free charge density will be 0, if there's a point over there, then the perpendicular component of the displacement field will also be 0. The surfaces that we are talking about are not the surfaces are not the material surfaces. They are not physical surfaces. They're just mathematical surfaces. They can overlap with the surface of your dielectric or not.
Potansiyel, yani Laplace denklemi yazdım. Free charge olmadığı için 0 oldu. Bounded charge'ı niye dikkate almıyorum?
You see, that is the advantage of taking the displacement field. You see, the divergence of the displacement field depends only on the free charges. That's why I'm working with the displacement field.
Bounded yüklerin bir potansiyeli yani niye hesap ediyor? Ona niye ciddi şey yapıyor?
Well, they are there. You see, they contribute to the electric field. Now, you see what we said over here in this example. Where was it? Yes. You see, the bound charges plus the free charges, they cause discontinuities in the electric field, the perpendicular component of the electric field. This is the perpendicular component of the electric field. This one, multiplied by a number that is different than 0 on one side of the surface, should be equal to the perpendicular component of the electric field on the other side. So the perpendicular component of the electric field is not continuous. That is telling me that there are bound charges there. It's already included. But when we are working with the displacement fields, the effect of bound charges are hidden in the displacement field. Because you remember, the displacement field is E epsilon 0 E plus P. And divergence of P is equal to minus the bound charges. So the effect of bound charges is already here in the displacement field. And their effect is in this parameter over here, permittivity. This is where the effects of the bound charges comes into the game. And now, since we know the potential, we can calculate the electric field, and from the electric field, we can calculate the bound charges, or we can directly use the fact that P is equal to epsilon 0 psi E times E. Well, we know E. These are just material properties, so we know P. These are tabulated. We know P, the polarization. Once we know the polarization, the surface charge density is just the normal component of P. So once we know P, we can calculate the surface charge and also the bound charge, if there are any, the volume charge. So the idea is we parameterize these effects of the bound charges on this parameter epsilon, permittivity, and using that relation, we can find the electric field, and once we know the electric field, we can determine the polarization and hence the bound charges. Any other questions? So let's give a 10-minute break, and then we can continue.